Today, I will be presenting our research on enhanced iris image security using pixel transformation and chaotic encryption. In an era where digital identity is everything, safeguarding biometric data is not just an option, it's a necessity. Today, I will walk you through a novel hybrid approach we've developed to protect iris templates from theft and unauthorized access. Let's start with the basics. Biometric security is the process of authenticating individuals based on unique biological traits, like fingerprints, facial structure, or the iris. Unlike passwords, you cannot change your biometrics if they are stolen, which makes security paramount. We focused specifically on iris recognition. Why? Because the iris contains complex random patterns that are stable throughout a person's life. It is widely considered one of the most accurate forms of identification. However, this high accuracy comes with a high risk. If an iris database is breached, the fallout is permanent. This brings us to the core problem. Stored iris templates, the digital files representing your eye, are vulnerable. They can be stolen from databases, intercepted during transmission, or even spoofed by attackers. Our objective with this research was clear. We wanted to design a security framework that makes an iris image completely unusable to an attacker, even if they manage to steal it. To achieve this, we proposed a dual-layer system. First, we scrambled the visual structure of the image, and second, we mathematically encrypt the data values using chaos theory. This ensures that the stolen data looks like nothing more than random digital noise. Now, you might ask, why not just use standard encryption? Existing approaches usually fall into two categories. Standard encryption, algorithms like AES, Advanced Encryption Standard, are incredibly secure for text, but they are often too slow for large biometric databases and fail to handle the high correlation between pixels in an image, visual cryptography. This involves splitting images into shares. While interesting, it often results in poor quality when the image is reconstructed and requires high bandwidth. The gap, most current systems lack sufficient randomness or entropy, making them susceptible to statistical attacks. Our research aims to fill this gap by introducing a method that is both highly random and computationally efficient. Here is the architecture of our proposed system. It functions as a pipeline. We take the original iris image as input. Step 1 is pixel transformation. This is where we shuffle the positions of the pixels. In cryptography, we call this confusion, breaking the relationship between a pixel and its neighbors. Step 2 is chaotic encryption. Here, we change the actual color values of the pixels using a chaotic map. This is called diffusion. The output is a cipher image that looks like static noise. This two-step process ensures that an attacker has to break both the position scrambling and the value encryption to retrieve the original biometric data. Let's dig deeper into the first step. Pixel transformation. In a normal photo, if a pixel is blue, its neighbor is likely blue too. This correlation allows attackers to guess image content. Our transformation algorithm rearranges the XY coordinates of every pixel based on a secret key. It's like taking a jigsaw puzzle and scattering the pieces across the table. We haven't changed the picture on the pieces yet, but we've destroyed the structure. This serves as our first line of defense. The second step is the mathematical heavy lifting chaotic encryption. We utilize a modified logistic map. Without getting too bogged down in the math, a logistic map is a mathematical function that generates a sequence of numbers that appear random but are deterministic if you have the key. The formula you see on the screen generates our encryption keys. The most critical feature here is key sensitivity. Chaotic systems are sensitive to initial conditions. If an attacker guesses the key but is off by even a tiny fraction, say, the entire generated sequence changes completely. This makes the system incredibly resistant to hacking. To prove our system works, we didn't just look at the pictures, we measured the math. We used a standard iris dataset and applied 3 key metrics. Entropy, this measures randomness. An image that is perfectly random has an entropy of 8. Our system achieves values very close to this ideal. Correlation, we want the relationship between pixels to be 0. This means knowing one pixel tells you absolutely nothing about the next. Sensitivity, NPCR and UHCI. These are complex acronyms that essentially mean if I change one single pixel in the original image, does the entire encrypted image change? The answer for our system is yes, which prevents differential attacks. Here are the visual results. On the left, you see the original iris scan, clear and identifiable. In the middle, the encrypted image. As you can see, it is unrecognizable static. On the right, look at the histogram. The top histogram shows the original image, peaks and valleys representing distinct features. The bottom histogram shows the encrypted version. It is perfectly flat, uniform. This flatness is crucial. It means every pixel value appears with equal frequency, giving an attacker no statistical clues to work with. Summarizing the security strength. Brute force resistance, because our key space is governed by chaotic parameters with high precision. Trying every possible key would take billions of years. Statistical resistance. As shown by the histogram, there are no patterns for an algorithm to latch on to. High sensitivity. The system is extremely volatile to changes in the key or the plain image, ensuring robustness against sophisticated cryptanalysis. In conclusion, our proposed hybrid method offers a significant step forward for biometric security. By combining pixel scrambling, transformation with the unpredictability of chaos theory, encryption, we have created a shield that preserves the confidentiality of iris data. Our experiments prove that this method outperforms many existing works in terms of randomness and resistance to attacks. Looking ahead, there are several exciting directions for this work. Real-time processing. We want to optimize the code to run instantly on security cameras. Multimodal systems, applying the same encryption to fingerprints and face scans simultaneously. Cloud deployment, securing massive national ID databases stored in the cloud. Mobile integration, adapting the algorithm to run efficiently on smartphones. Here are the key references that supported our research, including foundational work on chaos theory and the AE standard. Thank you very much for your time.